Hello everyone, I'm Andreu Cecilia and today I will be defending my PhD thesis with title Advances in Nonlinear Observer Design for State and Parameter Estimation in Energy Systems. So this presentation is mainly separated into blocks. First, I will present the theory related to observer design for a generic nonlinear systems. How can you add filters in this observer to reduce the effect of measurement noise? And how can you adaptive redesign this observer to reduce the effect of parametric uncertainty? Then I will focus on the practical applications that have motivated this new theory. First, I will solve a cybersecurity problem in DC microgrids and a monitoring problem in PEM fuel cells. So to understand the motivation of this thesis, it is important to understand the current tendencies in the energy sector. We're changing the way that we generate energy and distribute energy. First, we're introducing more and more renewable sources in our grid. Moreover, we are moving from a centralized market to a distributed market with more small regional distribution and more active consumers. In this context, energy systems can be understood as complex dynamical systems that have to be controlled and monitored to guarantee security, stability, and reliability. In order to develop these algorithms, a crucial limitation is that the technical, economical, and physical constraints limit the amount of sensors that you can place in the system. Therefore, during the evolution of these systems, there will be an evolution of internal unmeasured states that have to be monitored and controlled to guarantee this security, stability, and reliability. In order to develop these monitor and control algorithms, it is crucial to deploy an auxiliary algorithm that estimates these internal unmeasured variables from the measured signals. In the control theory context, a really powerful algorithm that you can use to solve this problem are observers. The idea of observer is not new. Actually, it was created more than 50 years ago, and the complete case for linear systems is well understood. Nonetheless, taking into account the new complexities in energy systems, it is important to develop or use more advanced observer theory and even extend the available theory. Taking into account this PhD thesis focuses on developing an observer design framework that can be implemented in systems with strong nonlinearities, significant amount of sensor noise, and parametric uncertainty, and show that this framework can be used to solve practical applications in energy systems. So let's start by introducing the theory related to observer design for a generic nonlinear system. So this PhD thesis operates under the state space formalism, which means that the dynamics of the system are depicted through a set of differential equations of this form, where x is the state vector, u is the control input, and y is the measured output. It is assumed that the state vector is unknown and that the control input and the measured outputs are known. So the problem that we are trying to solve here is to develop an algorithm that, from the information of the measured output trajectories, can reconstruct the unknown trajectories of the state. And the algorithm that we are going to use to solve this problem is an observer. The formal definition of an observer that we use in this thesis is the following one. An observer is a set of differential equations of this form that has a feedback term that is related to the error between the measured output and an estimation of this output. It is said that this set of dynamics is an observer if the estimation of the states converges to the true trajectories of the states. So basically, an observer design process is a process of designing a set of dynamics such that the state estimation error converges to zero. This is a stability problem that can be analyzed through Lyapunov theory. It should be mentioned that it is not the aim of this presentation to do an in-depth review of all the techniques that can be developed following this framework. Here, I will only focus on the two techniques studied in this PhD thesis, namely the high-gain observer and the parameter estimation-based observer. So let's start with the high-gain observer. The idea is to begin with a system in this triangular form here, where x1, x2, x3 are the components of the state. So we have this chain of integrator, and y is the measured output. It should be remarked that the high-gain observer is not restricted to this particular triangular structure. It can be generalized to other triangular structures. So the high-gain observer idea is to then take a copy of this triangular structure and add a feedback term that is the error between the measured output and estimation of this output multiplied by some constants to be tuned. The tuning of these constants is relatively easy. These alphas has to be tuned such this polynomial here is Hurwitz, and bar epsilon has to be small enough to guarantee stability. Moreover, as you reduce more and more the value of bar epsilon, you increase the convergence rate and robustness of the algorithm. The simplicity in the design and analysis of the high-gain observer has motivated plenty of control and monitoring techniques. However, this high-gain observer is not free of drawbacks. And to understand the drawbacks of the observer, here in this slide, I have depicted an example of a high-gain observer estimation. So in the blue line, it is the evolution of the true state of some system, and the other lines depict the estimation of the same high-gain observer with different values of bar epsilon. We can see that as we reduce bar epsilon, we're increasing what is known as the peaking phenomena. That is this sudden increase in the states during the transient. Moreover, if we repeat this simulation, but now we add some small persistent noise in the measured output, what we see is that by reducing the value of bar epsilon, we're increasing the noise sensitivity of the algorithm. So these are the typical drawbacks of the high-gain observer, but in this section, I want to focus on the peaking phenomena. Why? Because this sudden increase in the state estimation may be really dangerous in practice. And this is why most authors, when they develop observers for energy systems, they skip the high-gain observers and use alternatives. And this is a pity because there is a lot of techniques that are based on high-gain observers. Fortunately, some authors have proposed modifications in the standard high-gain observer that practically solves this peaking phenomena. In my opinion, the most promising result is the one presented in this paper depicted in the slide, creating what is known as a low-power peaking-free observer. So to understand the idea of this observer, here I have written the structure of a standard high-gain observer. That is just this interconnection of blocks where x1 hat is an estimation of the first state, x2 hat is estimation of the second state, and so on. So the first step in this observer is to duplicate the amount of states in the observer. So now, not only we have the x1 hat, x2 hat, x3 hat states, now we have some virtual states, eta 1, eta 2, eta 3, and so on, that are just a duplicate. So eta 1 also estimates x2, the second state, eta 2 also estimates the third state, and so on. It can be shown that this structure has mostly the same properties as the standard high-gain observer. But the advantage of adding these virtual states is that now what you can do is saturate the virtual states. And with that, you can actually show that robustness and convergence rate of high-gain observer prevails, but also by saturating the virtual states, the non-virtual states, the x1 hat, x2 hat, and so on, do not peak. So you have practically solved the peaking phenomenon. Now there is all these techniques that can be implemented in energy systems. So now I will jump to the second family of observers, that is the parameter estimation-based observer. The idea of this observer is to take the initial estimation error of the algorithm as a constant parameter to estimate. And if you are able to estimate it, then you can use this information to simulate forward in time the model and retrieve the two values of the state. Naturally, estimating the initial estimation error of a generic nonlinear system is an unfeasible task, but as proposed in this paper here, if the system is in a state-affine form, there is a pretty efficient solution. And the solution can be summarized as follows. The idea is to first take an open loop copy of your system with some state z. And with that, you can define estimation error between the true value of the states t and the open loop copy z. If you write the dynamics of this estimation error, you get a linear system as depicted in this slide. And as this system is linear, there's actually an analytical solution that is the fundamental matrix multiplied by the initial estimation error. The idea then is to take this initial estimation error as a constant parameter theta hat, that if you're able to estimate it, then you can retrieve the true values of the states using the last equation of this slide. The only thing that remains is how to estimate these parameters theta hat. And what this paper here proposes is to exploit the fact that the output equation is linear. With that, you can define a factor n like this, which can be shown that satisfies a linear regression as shown in this slide, where n is a known factor, c is also a known factor, and theta is a vector of unknown parameters to estimate. Actually, there is plenty of algorithms that you can use to solve this linear regression estimation problem. And if you look at any adaptive control book, you will find that you can solve this estimation problem through a standard gradient descent. That is the set of dynamics depicted in this slide. Then it can be shown that the parameter estimation of the standard gradient descent converges to the set omega depicted in this slide. That is basically the set of parameters in which the estimation of the output converges to the value of the measured output. It should be mentioned that converging to the set omega is not the same as saying that the parameter estimation has converged to the true value. To guarantee this parameter estimation convergence, it is crucial to add an extra condition, that is the persistence of excitation condition, which means that the regressor vector C satisfies this integral in here. With that, you can actually show that the parameter estimation converges to the true value of the parameter. The advantage of the parameter estimation-based observer is that in recent years, some authors have proposed alternatives to the standard gradient descent that relaxes this persistence of excitation condition. So with that, you can design observers that can be implemented in systems with low observability, meaning in cases where this excitation condition is not satisfied. Following this line of thought, what this PhD thesis proposes is to substitute the standard gradient descent by a natural gradient descent that satisfies some local geometry to be imposed. Roughly speaking, what you do is pre-multiply the standard gradient descent by the inverse of the Hessian of some function to be designed. What you can show with that is that the estimation not only converges to the set omega as the standard gradient descent, but optimizes this function here, creating what is referred as an implicitly regularized observer. To see the advantage of this new structure, let's consider a case where you don't have excitation. In such a scenario, the standard gradient descent converges to the set of parameters omega. If you implement the implicitly regularized observer, then you converge to the subset of omega that minimizes this convex function. So you improve the quality of the estimation. So up to this point, I have presented two families of observers that can be implemented in nonlinear systems. And all the theory related to the stability conditions, how to design these observers is explained in the manuscript. The theory is really nice, but when you try to implement this in practice, you have to take into account some extra elements. Precisely, you have to take into account that your sensors will not be perfect. You cannot perfectly measure your system, and your sensor will always have some unknown noise. Moreover, you have to consider that your mathematical model of the system is not perfect. There is always some discrepancy between your model and reality. So you have to consider that there is always uncertainty in your mathematical model. If you consider that you have noise and uncertainty, the quality of the observer estimation is affected. And it's the objective of the designer to reduce the effect of these unmodeled elements on the performance of the observer. For this reason, next slides will focus on providing some new techniques in order to reduce the effect of noise and uncertainty on the quality of the estimation. It should be remarked that these techniques follow a redesign philosophy, meaning that they assume that there is an already designed observer and modifies this observer in order to reduce the effect of the unmodeled elements. So in the next section, I will focus on introducing the idea of adding filters in observers in order to reduce the effect of measurement noise. It should be mentioned that this section has been made in collaboration with the Laguerre group at University of Lyon. So the idea is pretty straightforward. Here we consider that we have an observer and the input of the observer is the output estimation error. That is the error between the estimation of the output and the measured output. And we assume that the measured output is corrupted by some unknown noise depicted here with the factor V. So the filter solution is to add some filter dynamics in the observer in order to reduce the amount of noise that is introduced in the observer. This is a pretty straightforward solution, and basically most practical applications implement some type of filter in this form. The thing is that in the pure observer context, this architecture here is wrong. Why? Because what you are doing here is comparing the filtered output with an estimation of the unfiltered output. So you are comparing signals that are not the same. And this discrepancy introduces some error in the observer estimation. In order to eliminate this discrepancy, what you need to do is to add the filter dynamics in the observer. So now you're actually comparing the filter output with an estimation of the filter output. And if you write these equations, you will see that this is the same as filtering the output estimation error. So the main message here is that if you want to implement filters in observers, do not filter the noisy signal, filter the output estimation error of that signal. The thing is that now with this new architecture, even if the original filter and the original observer were stable, this coupling here might be unstable. This is why the next slides will focus on presenting some types of different type of filters and providing the conditions in which this architecture here is stable. So let's begin with the most common filter, that is the low-pass filter, which is the one that you want to implement when the noise is characterized by being of high frequency. This PhD thesis considers a pretty general low-pass filter with relative degree 1. So to understand the dynamics of this filter, here we have two sets of variables. We have some Z tilde dynamics, where Z tilde is the signal that you use in the observer, and we can see that in this dynamics there is the output estimation error Y tilde. This is why we say that this is a relative degree 1 filter. Moreover, the filter includes some internal dynamics, nu tilde, that add some design freedom in the filter. As mentioned before, the objective is to find the conditions in which this coupling here generates a stable structure. And what this PhD thesis was able to find is that under some very mild assumptions on the original observers, indeed, the assumptions of linear input to state stability gain with respect to the noise and a particular output growth condition, it should be mentioned that these are not restrictive. A lot of observers satisfy these conditions. Then, if the original observer satisfies these, you can always tune the filter to guarantee stability. And the tuning is summarized in this slide. To get an intuition of this parameter tuning, let's focus on three factors. First, we have this pH is equal to B transpose condition. This is a particular matching condition between the Z tilde dynamics and the internal dynamics of the filter. Moreover, we have this FP plus PF transpose condition, which means that the internal dynamics of the filter are stable. And finally, we have the condition of Q bar has to be large enough, that this means that the filter has to be fast enough in order to guarantee stability. Now I will jump to a second type of filter. Here I consider a different scenario. Instead of assuming that we have noise that is characterized of being of high frequency, now we assume that we have some measurement disturbance that is generated through a linear exosystem of this form, where we have some internal variable W and some matrices S gamma as depicted in this slide. The idea is to introduce what will be referred as an internal model filter. That is a filter that includes the information of this exosystem in order to exactly reject the disturbance before it enters the observer. The equations of the filter are summarized in this slide here. So we see that the internal model filter is a relative degree 0 linear filter with only two parameters to be tuned. We have some matrix phi that has to be tuned so the minimal polynomial coincides with the one of the matrix S from the exosystem, and the factor n that has to be tuned such the pair phi n is controllable. If you tune the parameters in this way, what you are actually doing is placing the zeros of the filter at the frequencies of the disturbance. So you block the disturbance before it enters the observer and you eliminate the disturbance. As you are blocking certain frequencies, it is crucial to establish the conditions in which this coupling here is stable. And this PhD thesis has the complete case for linear systems. So here, by looking the left-hand side of the slide, let's assume that we have a linear system with some matrices A, B, and C, and assume that the output function is corrupted by the linear exosystem depicted before. And now, by looking in the right-hand side, let's assume that we have a linear Leuenberger observer for this system, but instead of implementing the output estimation error, we implement the signal Z generated by the internal model filter. In such a scenario, if the pair SC is detectable and the spectrum of the matrix A from the system is disjoint from the spectrum of the matrix S from the linear exosystem, this means that the matrix A and the matrix S has no coinciding eigenvalues. Under these conditions, which are not restrictive, this thesis was able to find that if this matrix here is Hurwitz, then the internal model filter exactly rejects the disturbance and the state estimation error converges to 0. So now I will jump to a third type of filter, that is the dynamic dead zone filter. It should be mentioned that different from the other filters considered before, this is not a new idea. It was actually proposed by this paper represented in this slide. So we have this dead zone function. This is a function characterized by some amplitude, and when the input signal falls inside the output, the amplitude, the output signal is 0. And we are going to say that this depth zone function is dynamic because we are dynamically adapting the amplitude according to this set of dynamics here. So the idea is pretty straightforward, is to take this dynamic depth zone function in order to filter the output estimation error of the observer. And I thought that it was interesting to include this result in the thesis because by following the paper presented here, you can actually show that under the same assumptions and as in the proposed low-pass filter observer, indeed, meaning that the observer satisfies a linear input to state stable condition and a particular output growth condition, then you can always tune the dynamic depth zone filter to guarantee the stability of the coupling. And this is an interesting result because with that, what you can actually show is that you can combine these dynamic depth zone filters with the proposed low-pass filter to get really powerful filters. So now I have presented a framework on how to add different type of filters in observers in order to reduce different type of measurement noise. Now I will jump to the idea of adaptive redesigning an observer to reduce the effect of parametric uncertainty. So to understand the problem that we are considering here, let's assume that we have a nonlinear system depicted by the dynamics in this slide, where theta is a vector of parameters. And let's assume that we have an observer designed for this system. Naturally, this observer depends on the vector of parameters theta. The thing is that if this vector of parameters theta is not known, then you cannot implement the observer. A pretty straightforward solution to this problem would be to say, okay, as I don't know the parameters theta, I just plug in there a 0 and try to design the feedback term so this discrepancy between the model and reality is reduced. This is what you do when you do robust observer design. The problem with this approach is that robust observer usually requires increasing the gain of the feedback term. Therefore, you are increasing the noise sensitivity of the algorithm following a well-known trade-off between noise sensitivity and disturbance rejection. Moreover, robust observers provide no information about the unknown parameters. This is why, in this thesis, we explored an alternative known as adaptive observer redesign. The idea is to couple the observer with an algorithm that generates a parameter estimation theta hat, such that this function depicted in this slide converges to 0. If you are able to find this algorithm under some assumption, you can design the observer using this theta hat estimation, and under some conditions show that then the state estimation converges to the true value. This is a pretty powerful solution. The only thing that remains is how to design this algorithm that generates the parameter estimation. And this thesis explores two approaches. One that is referred as direct adaptive observer redesign, and another that is referred as indirect adaptive observer redesign. So let's just start by the direct approach. So let's assume that we have a nonlinear system depicted by the set of dynamics in this slide. And let's assume that we have an observer that asymptotically converges to the true value when the parameters are known. This means that there is a radially bounded Lyapunov function, the derivative of which is upper bounded by a strictly negative factor and some factor that depends on the unknown parameters. So the direct adaptive redesign idea is to design some parameter adaptation dynamics such that this factor that depends on the unknown parameters is eliminated from the Lyapunov function derivative. In order to design such parameter adaptation dynamics, there is a crucial assumption that is the existence of some function g that satisfies the last equation in this slide. If you are able to find this function g, then you can design the parameter estimation dynamics as depicted in this slide here, and show that the state estimation error converges to 0, and if you add an extra system of excitation condition, that the parameter estimation error also converges to 0. This is a powerful result, but it should be mentioned that is not a new result. There is some papers that add the proof of this result. In this slide, I have included some of these papers. But it should be remarked that all these proofs are based on a combination of a weak Lyapunov function, weak in the sense that its derivative is only non-positive, and the Barbalat's lemma. This detail will be important for later. So here we have a solution to this parametric uncertainty problem. But when you try to implement this direct adaptive redesign idea in practice, some issues start to appear. And the issues detected by this PhD thesis are the following ones. First, as the proof is based on a weak Lyapunov function, then there is no theoretical guarantees that the algorithm converges when there is measurement noise and uncertainty. Therefore, there is no theoretical guarantees that you can implement this observer in practice. This is a critical issue. A second issue is that finding that function g for the parameter adaptation dynamic implicitly requires the system being relative to degree 1 with respect to the known parameters. This means that all the unknown parameters appears in the first derivative of the output. And finally, in some scenarios, the functions that compose the regressor vector phi are unknown. For these reasons, next slides will focus on providing some solutions to these problems. First, a strictly Lyapunov function will be constructed. Second, a Huygens observer modification will be proposed to solve this relative degree issue. And finally, a new direct adaptive observer redesign will be proposed for cases where the functions in the regressor vector are unknown. So let's start by constructing a strictly Lyapunov function. So let's assume that we have a nonlinear system with the equations depicted in this slide, and let's assume that we have an observer, the stability of which can be proven through a quadratic Lyapunov function. Then, if we define a pair of functions lambda and epsilon, as in the end of this slide, what this PhD thesis was able to find is that this function b1 in here in this slide, which satisfies the common conditions for Lyapunov function, meaning that it is radially bounded and so on. So this function here, if alpha is large enough and the regressor vector is persistently exciting, its derivative is strictly negative. So this can be used as a strictly Lyapunov function to have theoretical guarantees that the direct adaptive redesign converges in presence of noise and uncertainty. So now we have theoretical guarantees that we can implement this in practice. It should be remarked that this proof is based on the assumption that the regressor vector is persistently excited. If you have no excitation, then we don't have guarantees that this algorithm converges in practice. Now let's try to address the relative degree limitation. So the relative degree problem can be understood as a sensor selection problem. Let's imagine that we have a practical application with multiple sensors, and one of these sensors is relative degree 1 with respect to the known parameters. In such case, we would select that sensor in order to design the direct adaptive observer. The problem is that in a lot of cases, you don't have multiple sensors, you have only one sensor, and such sensor may not satisfy this relative degree condition. So what this thesis proposes in such a scenario is to design an auxiliary signal Z that satisfies the relative degree condition and then design the direct adaptive observer using this auxiliary signal Z. Naturally, as this is not a signal that is measured, what this thesis proposes is deploying a secondary Huygens observer that estimates this auxiliary signal. And then you couple the Huygens observer and the adaptive observer in a way that guarantees that the state estimation and the parameter estimation converges to the true value. In this new architecture, the only thing that remains is how to design this auxiliary signal. And what this thesis proposes is the following one. So if we assume that the nonlinear system is described by this set of equations in this slide, and we parameterize the auxiliary signal as depicted in this slide, then we say that the auxiliary signal is adequate if it satisfies three conditions. First, that it satisfies a particular matching condition. This means that the system, the auxiliary signal is relative degree 1 with respect to the parameters. Second, that you can design an observer taking the auxiliary signal as the measured output. And finally, that there is a map T that relates the output and its derivative up to some degree with the auxiliary signal. So with the first two conditions, what you are saying is that you can design a direct adaptive observer taking the auxiliary signal as the measured output. And with the last condition, what you are saying is that you can robustly estimate the auxiliary signal through a Huygens observer. Indeed, the architecture that this thesis proposes is the following one. The idea is to deploy a Huygens observer that estimates the output and its derivative up to some degree. Then you are going to use this estimation in the map T to reconstruct the auxiliary signal. And then you're going to use this reconstructed auxiliary signal to design the direct adaptive observer. It should be mentioned that there is a coupling between the Huygens observer and the adaptive observer, because the x hat and theta hat estimations of the adaptive observer are used in the Huygens observer. Proving the stability of this coupling was not an easy task. Nonetheless, by exploiting the strict Lyapunov function result presented before, you can actually prove the stability through a small gain argument. This is why having a strict Lyapunov functions have practical and theoretical interest. Indeed, the result is that if the regressor vector satisfies a persistent of excitation condition, then you can always tune the high gain observer in order to ensure that the state estimation error and the parameter estimation error converges to zero. Finally, I will jump to the case where some functions in the regressor vector are unknown. So the scenario that we are considering here is that we have a nonlinear system with equations depicted in this slide where phi is the regressor vector and theta is the vector of unknown parameters. And here we assume that the functions that appears in phi are unknown. What we have is a library of potential candidate functions. So for example, let's imagine a case where phi only have 3 functions that we don't know which are, and we have a library of 20 potential candidates that only 2 truly appears in the systems and the other ones do not appear in your system. In such case, you can rewrite the system using this library as the regressor vector, and you will have a new vector of parameters theta s that is of much larger dimension. So what this thesis proposes is to then design a direct adaptive observer to directly estimate theta s instead of the parameter theta. So this is a pretty powerful result because what you're doing here is not only estimating the unknown parameters, but discovering the functions that appears in your system. This is an interesting result, but in practice you cannot implement it. Why? Because as this library has more functions than reality, you will have an over-complete regressor. Therefore, in general, for any system trajectory, there will be multiple function combinations that can explain that system trajectory. Therefore, this over-complete regressor can never be persistently excited. And as explained before, persistence of excitation was a necessary condition to guarantee, a sufficient condition to guarantee convergence of the direct adaptive observer. This is why there was an interest on developing an alternative direct adaptive observer that can be implemented in such a scenario. And the proposal of this thesis was the result of the following line of thought. So we know that the optimal value of theta s has a lot of zeros because only a small selection of functions truly appears in your system. Therefore, we want a parameter estimation dynamics that promotes sparse solutions. And by looking at the literature of sparse signal recovery or compressed sensing, you can find that you can promote a sparse solution if you optimize the L1 norm of your estimation. Therefore, what we want to do is to design an alternative direct adaptive observer redesign that implicitly optimizes an L1 norm. Notice that this is very similar as what we did in the implicitly regularized observer. So here we can implement a similar result. What we are going to do is pre-multiply the function g of direct adaptive redesign by the inverse of the Hessian of some function that is close to the L1 norm. What you can show with that is that not only you are eliminating the unknown factors from the Lyapunov function derivative, but you are promoting a sparse solution. So you can discover the functions that appears in your system, even if you have an over-complete regressor. So up to this point, I have presented the direct adaptive observer redesign that is based on eliminating the unknown factors from the Lyapunov function derivative. This is a powerful result, but in some applications, even if you find this function g, it may be possible that during the design, you change your model and your observer, and then you need to redo again all the direct adaptive observer redesign. And this may be unfeasible in some applications. This is why in some cases, it is interesting to have some parameter estimation dynamics that are somewhat decoupled from the observer design process. And this is what you can achieve following the indirect adaptive observer redesign. The idea is to begin with an observer that satisfies an ultimate bound condition with respect to the parameter estimation error. This is not a restrictive assumption. And what you do is deploy a parameter estimation dynamics that is ultimately bounded by the state estimation error. If you find this parameter estimation dynamics, then you can prove that the coupling between the observer and the parameter estimator is stable through a small gain argument. The only thing that remains is how to design this parameter estimation dynamics. And what this PhD PhD thesis proposes is to implement an immersion and invariance approach. So roughly speaking, the idea is to estimate the parameters through the set of equations depicted in this slide, where only one function has to be designed. That is this function beta that has to be designed such that this dynamic Z here has an origin that is asymptotically stable. If you are able to find this function beta, then you can prove the stability of the coupling through a small gain argument. So up to this point, I have presented the theory on how to design observers for a generic nonlinear system and how can you redesign these observers to reduce the effect of measurement noise and parametric uncertainty. Now I will jump to the practical applications in energy system that has motivated this new theory. First of all, I will solve a cybersecurity problems in DC microgrids. It should be mentioned that this part has been made in collaboration with the Aalborg University and the Technical University of Denmark. So first of all, it is interesting to understand why there is a cybersecurity problem in DC microgrid. The thing is that we are changing the way that we generate and distribute energy. We are moving from a framework where you only have a centralized generating unit that generates the energy that you send to the whole country to a framework where you have distributed generating units that are interconnected following some topology. For example, let's imagine that you have at some place some solar panels that are connected to a set of batteries in another place that are connected to a set of electrolyzers that generates hydrogen in another place. So you have this network of distributed generating units. In this new framework, a critical issue is guaranteeing the optimal regulation of current, voltage, and energy shared between agents. And this is basically a control problem that has been addressed in the literature. And original results in the literature assume a centralized framework, meaning that they assume that you have a bunch of sensors in your system, that these sensors send the information to a centralized aggregator that did all the computations and send back the information, the feedback terms, to the agents. The problem with this architecture is that it does not scale well. So let's imagine that we have a system with 1,000 agents. What you need to do is to send the information of 1,000 agents to a centralized aggregator that needs to do the computation of 1,000 agents and send back the information to 1,000 agents. So this has to operate in real time. Obviously, this is not practical, and this is why most modern control solutions assume a distributed framework in which each agent of the system has a local control unit, and then you have a cyber layer of communication links between the agents. With that, you eliminate the centralized aggregator and you solve these scalability issues. The problem with this new architecture is that now you have opened up the possibility of attacking the local sensors at each agent or the communication links that communicate neighbor agents. And actually, by attacking a sparse selection of sensors and communication links, you can unstabilize the whole microgrid. This is why there is an interest on developing algorithms that can detect and mitigate such attacks. Indeed, this PhD thesis focuses on a DC microgrid, which has a control algorithm that requires measuring the local current at each converter and sending this current information through a communication link. Therefore, there is a possibility of attacking the local current sensor or the communication link that sends this current information. And the objective is not only to develop an algorithm that can detect this attack, but can estimate the value of the attack signal. Why? Because if you are able to get this information, then you can use this value to mitigate the effect of the attack on the microgrid. Precisely, this PhD thesis models each agent of the system through the set of equations depicted in this slide. It should be mentioned that there is actually plenty of literature related to attack detection and mitigation in DC microgrids. But the main difference between all this literature and what we are doing here is that now we assume that each agent has to provide some local energy that is modeled as a constant power load with unknown power. And this is a critical difference because by considering the constant power load, now there is a strong nonlinearity in the model with an uncertain parameter. Therefore, all this literature that assumes that the model is linear can no longer be implemented in this case. And what we need to do is implement nonlinear observer theory. And this is what this PhD thesis proposes. And the line of thought follows the following reasoning. So by reorganizing the equations presented before, you can see that you can actually reconstruct the local current if you know the voltage derivative, the unknown line currents, and the unknown constant power load. And if you are able to reconstruct the current, then you can estimate the stack by comparing your measurements with your current reconstruction. So actually the attack, detection, estimation, and mitigation problem is a problem of estimating the unknown voltage derivative, the unknown line currents, and the unknown constant power load. This is a state and parameter estimation problem that can be solved using the theory presented in this thesis. It should be remarked that this is not a trivial problem because here we are considering a really large-scale system with strong nonlinearities and uncertainty. This is why here what we are going to implement is a distributed observer, meaning that we are going to develop an observer that you place at each agent of the system, and then you are going to communicate neighbor observers in order to guarantee stability. Precisely, the structure of the observer that you place at each agent of the system is summarized in this slide. So the observer is an interconnection of three subsystems. We have a low power observer that estimates the voltage derivative and an auxiliary signal that you are going to send to a Leuenberger observer to estimate the unknown line currents, and this information is sent to an immersion invariance parameter estimator to estimate the unknown constant power load. It should be remarked that this parameter estimator follows the indirect adaptive redesign presented before. And this observer only operates using the local voltage sensor and the neighbor observer estimation. With that, you can reconstruct the local current and use this information to estimate the attack and mitigate its effect. This attack estimation mitigation strategy has been validated through a set of numerical simulations. In this slide, it is summarized the result of one simulation. So what we considered here is a small microgrid of 8 agents that are interconnected following this topology here. And we deployed an algorithm, control algorithm, that guarantees consensus between the agents. We see that after some transient in the first figure, we can see that the generated current and the voltage current converges to the same value. Therefore, this control algorithm guarantees consensus. But after the time 4 seconds, there is a sequence of attack that we can see that drastically modifies the performance of the system, and it even destabilizes the load voltage. So in a second simulation, what we did is deploy the proposed observer at each agent of the system and deploy the mitigation strategy. And we can see that our algorithm is able to immediately detect and mitigate the attack on the system. So numerical simulations are really nice, but does this type of strategy work in practice? So we were able to validate this strategy in an experimental prototype at University of Aalborg. There we had a small microgrid of 2 converters that have constant power loads and some consensus algorithm. And we wanted to study the performance of our approach with a different type of cyber attacks. So we consider first a constant cyber attack that in the first figure in here, we can see that drastically modifies the performance of the system. Moreover, we considered a RAM cyber attack and a sinusoidal cyber attack. We can see that they also drastically modifies the performance of the system. And we studied the performance of our algorithm in this system with that cyber attack. And in this slide, it is depicted the result of 3 experiments. So in the first experiment, what we did is first implement a change in the constant power load of the converters. We see that this change modifies the set point of the system. This is not a problem. Actually, you want the set point of the system to be modified. The important thing to notice here is that changing the constant power load is not detected as a cyber attack and is tried to be mitigated. This is important because this shows that our algorithm actually adapts to changes in the unknown constant power load. And after that, we introduced a constant cyber attack that we can see that is immediately detected and mitigated. In the second experiment, we did something similar. First, we have a constant cyber attack, and then a change in the load, the constant power load. We see that everything still operates adequately, but now we have introduced a significant communication delay between the observers, and we see that everything still works correct. Therefore, the proposed strategy is somewhat resilient to communication delay. And finally, we study the performance under a RAM cyber attack and a sinusoidal cyber attack, and we see that everything still works adequately. So now I will present a second practical application that has motivated this theory. That is a monitoring problem in PEM fuel cells. Part of this section has been made in collaboration with the Energy System Design Laboratory at University of Alberta. So a polymer electrolyte membrane fuel cell is an electrochemical device that converts the chemical energy of hydrogen into electrical energy. The basic operation of this device is that you introduce hydrogen in the anode, which reaches a catalyst layer that separates this hydrogen into protons and electrons. This, due to the electrical properties of the membrane, only the protons can go through the membrane and the electrons are forced to go through an external circuit. This is what generates the electrical load of the device. Then these protons and electrons combine with oxygen in the cathode catalyst layer to generate water and heat. Naturally, this is a device with a lot of internal variables related to electrical processes, chemical processes, and thermal processes. And you cannot deploy sensors to measure all these internal variables. This is why there is an interest in developing observers to estimate all these internal variables. And this PhD thesis focuses on developing observers that can measure the water that is generated in the cathode catalyst layer. Why? Because this water is not only a byproduct that you can forget about, it's actually an element that has a significant impact on the performance of the system. Because if too much water accumulates in the fuel cell and the fuel cell starts flooding, then the reactants cannot efficiently reach the catalyst layer, which has a significant performance degradation effect and induces unstable output voltage. Moreover, if too much water is evacuated and the fuel cell starts drying, then you reduce the conductivity of the membrane, which increases the ohmic losses and accelerates degradation. So obviously, the water is a variable that you want to maintain inside some bounds. The problem is that you cannot directly measure this water. This is why this thesis proposes designing an observer to estimate these water variables. It should be remarked that fuel cell dynamics are related to models with strong nonlinearities and a significant amount of uncertainty. This is why it was crucial to deploy more advanced observer theory and even extend the available theory. So as a first step, in order to design the observer, it is crucial to have a model for the fuel cell system. And this thesis started from the governing equations that depicted the dynamics of the oxygen, the water vapor, the liquid water saturation, the water content, and the temperature. As these governing equations are described through partial differential equations, it is crucial to discretize the system in a set of control volumes to transform this to a set of ordinary differential equations. As the objective was to have a really low complexity model, we minimize the amount of control volumes. So we consider each channel as a single control volume, each porous media as a single control volume, and we separated the membrane in two control volumes. With that, we obtain a model in a state space form of dimension 13. It should be mentioned that this is really low complexity compared with the models that are used to design and validate fuel cells, but it's still too large to design nonlinear observers. This is why, as a second step, we reduce the order of this model in order to reduce the complexity. It should be mentioned that here we did not implement any model order reduction techniques. What we said is, okay, as the objective is to estimate the liquid water saturation in the cathode catalyst layer, what we are going to do is just eliminate all the variables that are not related to this liquid water. So with that, we obtain a second order nonlinear model with two states, that is the cathode porous media temperature and the liquid water saturation in the cathode porous media. Moreover, we have two inputs, that is the cathode air velocity and the exchange current, and two outputs, that is the cathode porous media temperature and stack voltage. These are the two signals that we can measure. Now that we have a really low complexity model, we can start developing observers. And actually what we found is that theoretically, we can design a high-gain observer only using the temperature signal. This is an interesting result, but we found that in practice, you cannot implement a standard high-gain observer. Why? Because on the one hand, in practice, the temperature sensors have some small persistent noise that is amplified by the high-gain observer. Moreover, even if this system here is observable in feasible conditions, feasible in the sense that the temperature has to be larger than 0 and the exchange current is non-zero, things like this, the standard high-gain observer, due to the peaking phenomena, its estimation may leave these reasonable conditions during the transient, and this makes the observer lose convergence. This is why this thesis proposes that instead of implementing a standard high-gain observer, to implement a low-power peaking-free observer in order to eliminate this peaking phenomena problem and reduce the effect of noise through dynamic dead zone filtering. So in this slide, it is summarized the architecture of the observer, and we validated the performance of this observer through a set of numerical simulation. The scheme of this simulation is summarized in this slide here. So what we have is a fuel cell model that is controlled through a PI controller that maintains the temperature at a constant value. And then we are going to excite this model through a set of current changes. This generates a temperature signal that is corrupted by some persistent unknown noise. And we use this noisy temperature signal in the observer to estimate the liquid water saturation. In this, the temperature profile that is used is the following one. So we can see that the temperature oscillates around some constant value, and we have some amount, a small amount of persistent noise in this signal. And here it is the result of the estimation. So in the yellow line, it is the true evolution of the liquid water saturation. And then we have the estimation of the proposed observer and a standard high-gain observer. We can see that the proposed observer not only does not peak, but significantly reduces the effect of the noise. So this performance is adequate, but actually there is an interesting detail. That is that the observer only uses the temperature signal. So we still have the voltage sensor that is not exploited in the observer. Intuitively, there is the idea that if you add extra information in the observer, the quality of the estimation should improve. And this is why we wanted to study what happens when we implement the voltage sensor in the proposed observer. It should be remarked that when you have a nonlinear observer already designed, trying to add extra sensors is not a feasible, reasonable or easy task. However, in this particular case, the voltage equation satisfies a particular monotonic condition with respect to the liquid water saturation. That is the condition depicted in the end of the slide. And we can exploit this condition to add the voltage sensor in the observer. Indeed, what this thesis was able to find is that if you have a system in a triangular form with respect to one output, Y1, so you can design a high-gain observer using this output. If you have a secondary output, Y2, that satisfies this monotonic condition, then you can modify this high-gain observer according to the last equation in this slide. So we exploited this result to add the voltage sensor in the observer. And we repeated the last simulation to see how much it improves the quality of the estimation. And here we see the same simulation as before, but instead of implementing a low-power peaking-free observer with dead zone, here we implemented a standard high-gain observer with the voltage sensor. And we can see that the performance of the system is drastically improved. On the one hand, we can see that the convergence rate is drastically improved, because before we required like 200 seconds to converge to the true value. But now we converge in less than 2 seconds. Moreover, we see that the noise sensitivity of the algorithm is drastically reduced. Intuitively, we can deduce that we see that this is the improvement appears because by exploiting the monotonic condition, the state estimation of the observer is pushed in the right direction during the transient. Therefore, we require less high-gain feedback terms, which drastically reduces the noise sensitivity of the algorithm. And finally, we proposed a last modification of the algorithm. That is that in practice, it is very difficult or impossible to measure the liquid water saturation. Designing experiments to estimate the parameters in the liquid water dynamics is also very difficult. This is why it's more reasonable to assume that these parameters are unknown. So what this thesis proposes is to do a direct adaptive redesign in this observer to estimate these parameters online. And this seems an interesting approach, but there is a difficulty. That is, if we rewrite the system equations as depicted in this slide and only take the temperature signal as the measured output, I will explain why we consider this later. So if we rewrite the system equations in this form, we can see that by multiplying the vector b by the vector c, we obtain 0. This means that these parameters are not relative degree 1 with respect to the measured output. Therefore, we cannot implement a direct adaptive redesign. Nonetheless, what we can do is to implement the high-gain observer modification proposed in this thesis. So we are going to deploy an auxiliary observer that estimates an auxiliary signal that is used to design the adaptive observer that estimates the liquid water saturation and the unknown parameters. And then we are going to couple these observers. In this architecture, there is two interesting details. First, that we are not using a standard high-gain observer, we are using a low-power dead zone observer. Why? Because it has higher performance, that's it. And the other is that this observer only uses the temperature signal. So we don't use the voltage signal. Actually, in practice, you can implement the voltage signal exploiting the monotonic condition, and you will drastically improve the performance of the system following as shown in the last slides. However, here we do not want to do that. Why? Because as in practice, it is very difficult to measure the liquid water saturation, we need some free signals to assess the quality of this estimation. This is why the observer only uses the temperature signal, and we have the voltage signal as a free signal that we are going to use to assess the quality of the estimation. And this is what we did when we validated this observer in an experimental prototype here in Institut de Robótica and Informática Industrial. So we had a PEM fuel cell with an open cathode architecture that is enclosed in an environmental chamber in order to make the experiment repetitable. And what we did is excite the system with some particular change in the current and the cathode air velocity in order to generate a temperature signal that is used in the observer. And indeed, this is the result of the experiment. So in the first figure, it is depicted the estimation of the liquid water saturation. And we can see that the estimation converges to some reasonable values. Nonetheless, as we cannot measure the liquid water saturation, we cannot compare this estimation with anything. Nonetheless, we can use the estimation of the liquid water and the estimation of the temperature to generate an estimation of the voltage signal. And we can see that this estimation converges to a relative error below the 0.4%. Therefore, as the observer did not use the voltage signal, but this estimation of the voltage signal has converged to the true value, we can conclude that the estimation of the observer is actually good. So as a conclusion, this PhD thesis has proposed a set of observers to solve practical applications in energy systems. First, multiple observers have been proposed to estimate liquid water saturation in PEM fuel cells. Moreover, an observer-based cyber attack detection and mitigation strategy has been developed for DC microgrids with unknown constant power loads. It has been established that these problems are related with models with strong nonlinearities, significant amount of sensor noise, and parametric uncertainty. And this has motivated the use of more advanced observer theory and even extend the available observer theory. First, a new framework to implement low-pass filter in nonlinear observers have been developed. Moreover, a new internal model filter has been proposed. Moreover, as for the first time, a strict Lyapunov function for direct adaptive observer has been designed, and this result has been exploited to solve a relative degree limitation of this type of observers. And finally, two new observers have been proposed. On the one hand, a new direct adaptive observer redesign that can be implemented in systems with over-complete regressors, and finally, an implicitly regularized observers. It should be mentioned that these results have concluded in a set of journal publications that are summarized in this slide here. Moreover, it has also concluded in a set of conference publications that are summarized in the following slide. It should be remarked that as the first part of the thesis focused on a generic nonlinear systems, the results can still be implemented to solve additional problems in other energy systems. For example, in future works, it may be interesting to estimate more internal variables in PEM fuel cells, for example, the membrane water content, or to solve different mitigation strategy in, for example, AC microgrids with different type of cyber attacks, so as man-in-the-middle attacks or replay attacks. It should be mentioned that the theory can still be extended. On the one hand, there is still the necessity of extending the internal model filter theory to the nonlinear case and use this to solve some PEM fuel cell problems. For example, it may be interesting to reduce the effect of anodic purges on the quality of the voltage signal. And finally, it should be interesting to relax the persistent of excitation condition in adaptive observer redesign. One line of work in this direction, it may be to exploit these natural gradient descent algorithms that implicitly optimizes some functions. And in parallel, it might be interesting to exploit some recent results proposed by Romeo Ortega that relaxes these persistent excitation conditions, but have not been implemented in direct adaptive observer redesign. So in this last slide, it is depicted the projects that made this PhD thesis possible, and this will be the end of the presentation. Thank you very much for your attention.